Okay, so thank you everybody for being here. So welcome to the series of online meetings entitled Advances in Socio-Epidemic Mathematical Modeling of the Italian Mathematical Union. So today we start this second cycle with an internationally renowned mathematician. So it is a great honor to host today Professor Eitan Tadmor from the University of Maryland. His career is more than outstanding, since he gave fundamental contributions in almost all fields of applied mathematics, and especially in kinetic equations and hyperbolic PDEs. Today, he will present the talk, Emergent Behavior in Collective Dynamics. So again, thank you, Eitan, and the stage now is yours.
Thank you, Maya, and thank you for the invitation. And for those who, hello from Paris to everybody who is joining in. And I apologize, I don't know how to make myself even more beautiful because it's so pale, but it is what it is. And let me start, since I mentioned Paris, by thanking the Foundation of Mathematics in Paris. I'm visiting the foundation for this year, and being hosted in the Jacques-Louis Lyon's laboratory. And I should also mention, of course, my affiliation with Maryland and the Navy that supports me for so many years. So I will give an overview on the mathematical aspect of emergent behavior in collective dynamics. And I think it's appropriate for this audience that I will start with a few examples. And the first example, okay, let me just move this, okay. The first couple of examples are taken from an Italian group. These are actually experiments of Starling and midgets. And basically, these are the object of interest. I should say at the start that, at least to my knowledge, the mathematical understanding is not at the level that can explain all the details beyond what we are seeing here. But at least there are several things which are important. In all the models that I will mention, the number of agents or particles is far below what is expected or usually we see in physics. So the models, the statistical physics arguments cannot be precise, and all the models are just approximate models. Nevertheless, we are able to ask, I think, at least understand the important questions that need to be asked. There is still a way to go between the math and this kind of experiments. And the example that I have in mind, let me classify them into three groups. We are dealing with agents. I will call them agents rather than particles, and I will classify them to living agents, for example, birds or fish, school of fish, or how cells form tissues, or thinking agents. Typically, it's human or some sort of motors or some evolution in a net. And then finally, non-living agents, and here are a few examples. So this is a rough classification of different kinds of agents, and I would like to unify and to present, of course, in a cartoon approach to take into account the different agents and the different scenarios. Later on, I will make a point that we cannot make just a unification for all these different cases. We have to get into the details. Now, what are the fundamental issues that we are after? First, we have a crowd of agents which are driven by different rules of pairwise interactions. So the rules, which are different, are the distinctive feature that make the different scenarios different from each other. And the rules falls into the category of alignment or synchronization, repulsion or attraction. There are no collisions. That's an important thing. And the reason that we do not look at collisions, but we look at terms like alignment, attraction, or repulsion is because the agents we are discussing are not particles. That's the reason I call them agents, but these are agents which have sensors and sensors. with which they probe the environment. So this is aspect number one. The second aspect is that these sensors and sensors, by definition, they are local. The interaction between agents and the environment are short-range interactions. Since when talking about short range, I have to define the notion of neighborhood. Since I have to define the notion of neighborhood, the geometry of the interaction is important. And then there are coherent structures that emerge for large time or large crowds, like we can call them flocks or consensus or swarm, whatever you. So there is an issue of going from local to the global effect, the formation of long-range structures or pattern. And this process going from local to global, this is the emergent behavior I'm looking at. And the fundamental question that I would like to address is how short-range interactions are self-organized into long-range and higher-order patterns. In fact, this is the main question to my taste that overrides collective dynamics. And we are still far from full understanding, but at least we know how to ask the right questions. So when I'm saying that we are far, the canonical example here of having a flock like that, to my best knowledge, I mean, we cannot explain by fundamentals this beautiful picture that we see. It requires more than just the fundamentals I will describe in this talk. So let me take a canonical example. I don't know if you see, because I don't see the title, it's covered, but and the canonical example, the paradigm here is a model for alignment, which goes after the name of Kucker-Smale. And it's a canonical example for these pairwise interactions between agents which have traits or properties or positions which I denote by P. The position is a generalized position. And the idea is that we have n agents and they interact in the following way. The rate of change of their position is given by a weighted average of the local fluctuations. So if we look at agent I, we sum all the differences between Pj and Pi. So these are the positions of all the neighbors. This is the position of agent I. The difference is viewed as the local fluctuation. And the weighted fluctuation, these are the coefficient, the scalar coefficient in this case, phi ij, which in fact encode what is the precise information that we put into these binary interactions. Now, the notion of neighborhood is written here. This is the script n. We take into account only the neighbors which belong to certain neighborhood. So it will have to be explored. And then we normalize everything by the number of agents which belong to that neighborhood. So this is basically what I described. We have a crowd of n agents. Here are the ingredients. They have properties or positions or traits. Tau is a scalar factor, scaling. We have pairwise interaction. And the phi ij, I will refer as the communication kernel or interaction kernel. So this is a function which depends on the two positions of agent I and agent j. This is where the modeling begins. Now, the neighborhood includes all the agents where the phi ij is different from 0. We will assume that the interaction is always positive. And what is encodes, what is being told in this model is that the active particles steer towards environmental averaging. So here's another key word that in this business of collective dynamics, environmental averaging. Practically all models have one feature or another which has this kind of environmental averaging. When we see what is written here, essentially, is each agent is replaced by sort of environmental averaging, weighted averaging, by the properties of its peers. Okay, here are 6 canonical examples that from completely different corners of science that fit into this framework. The first example that I would always like to start with is the bounded confidence model of Krause and Hexelman. It's a very simple model. It's a symbol of opinions. So the position are scalar numbers denoted here by P. Let's say opinions between 0 and 10. And the statement is that each person changes its opinion here by taking a weighted average of the fluctuation, the differences between its own opinion and the opinions of its neighbors namely neighbors in the sense that the difference of opinions is at most 1. You notice, of course, that we measure the notion of neighborhood by difference of opinion. This is valid as long as we are talking about scalar opinions, but already the first simple question, if we have vector of opinions, how do we quantify neighborhood, is non-trivial. So here is a very simple model, which falls into the category I mentioned before, simply with an interaction function, which is a radial function. It's the characteristic function of the interval 0, 1. That's exactly what we had before. And what we see here is a distribution of opinions along this y-axis, distribution of opinions between 0 and 10. The x-axis is the time. This is the interaction kernel, which is the characteristic function of the interval 0, 1. And we can see that as time goes on, the opinion starts to concentrate, and then at certain point, they concentrate to a point which is distance more than 1 between the different parties, and this would be the steady state. There is no consensus. What emerges in this case are 4 different parties of opinions. This is example 1. The second example deals with real positions. It comes from engineering. I try to mention few. I always make unhappy some people, but at least few relevant references in this context. Let's say in this case, it's the models. The model is the rendezvous model. Do you see the title of the slide, by the way? I don't see this.
Yeah,
Yes.
Okay, so I'm the only one. Oh, now I see. Okay, so this is a model for pedestrian or other sensor-based motions or robots. And we are talking about positions, and every agent has a, let's say, a 3-dimensional position. It changes its position by taking a weighted average of the usual fluctuation, in the sense that we take the difference in the positions here. And the fluctuation, the weights here are depend on the distance. In this case, we can justifiably call the weights metric. The only interesting thing is that this is not what happens in reality. The interaction, at least in pedestrians, it was observed, does not depend on the metric, but depends on the crowdedness. I interact with another agent. If I'm in position xi and there is another agent in position xj, in the context of pedestrian dynamics, the interaction depends on how crowded some control volume, which is enclosed between xi and xj, is, rather than the sheer metric. This is just to show you that the simplest metric dependence interaction is not always valid. So what we have here is a completely different kind of interaction, a radial interaction, depending on the number of agents. And the question is, that we would like to ask in the sense of emergence is, do these agents come together? So this is the rendezvous problem. And if we take now the characteristic function, which is on the interval 0, 1, we see that they do not. We start with some configuration of agents, and then they concentrate to some finite collection of, let's say, groups, period. So of course, the question is, when do they come together, at a finite time or infinite time? And here's an example. If we take phi to be 1 over r, then yes, they will always come together, and even at a finite time. So there's a finite time gathering if we change the rule of interaction to be 1 over r. So it's the first example that we see that the large time behavior depends now on the precise information in the rules of interaction. By the way, if phi is 1 over r, and you divide here by 1 over r, essentially it means that what we average is not the relative positions, but the relative orientations. It's independent of the distance. Of course, this is completely radial, and actually everything depends on visibility, and it becomes considerably more complicated. Anyhow, this is the second example. The third example that I chose is from a completely different topic, and it's so-called the ELO rating model, and it's named after Arpad ELO, a physicist who was a chess player and was interested in rating chess players. What we quantify here are the ratings of the players. Again, these are scalar quantities. We have n players. And the idea is that every two players, when they play, so the interaction is not deterministic, it's random. So they play against each other. There is an outcome for the play, and the outcome is either +1 or -1. So Sij plus Sji must be 0. And we change the rating of each player. Here it is. By some massaging on the original ELO's rating model, what we have there is something like that. We take the sum of all the interactions with other player. I'm talking now about player indexed with I, tagged with I. And we take a weighted average. Of course, this is the important thing of the interactions. And what we take in the weighted average is not the Qj minus Qi like we had before, but we can take here any odd function of the difference between Qj and Qi. If I remember correctly, in the ELO rating, the odd function was hyperbolic tangent. And plus, we have to take into account the outcome of the game, +1 or -1. So with some massage here, essentially, this is the ARPAD ELO and the rating model, which fits into this general framework that I'm trying to draw here. And the idea is that the expected value from the outcome from the game should more or less reflect the difference between the strengths, the intrinsic strengths of player I and player J. So we associate with each player intrinsic strengths, denoted here by rho. And we assume that as we play more and more, the difference in the strengths will be realized in the games. And then let me jump here. We should see that in this model, the rating should reflect the intrinsic strengths in the sense that the expected value of the rating should approach the strength. Indeed, this model was adopted by FIFA and other organizations, and I quoted here what is the actual interaction function that were quoted above. So this is the phi for FIDA, and this is the y for FIFA, and tau is some importance factor. All I wanted to take from this example is A, this is slightly different than social dynamics or engineering. B, that we see here that there is a role for external forcing, so the system is not closed. And C, that instead of taking the difference, we can take any odd function of the distance. Then there are recent works, by the way, I mentioned here the fundamental contribution of these authors for these models, is that they try not only to study the ratings, but they start to learn what the strength is from the model. So actually, what we propagate is not just the ratings, but the ratings and the strengths as well. So this was example number 3 of rating. Let me move to example number 4. This is about flocking. This is a seminal work from Cooker and Smale about the emergent behavior of flocks. And here we are considering velocities, and they fit into the general framework that I mentioned before. But this is a second order model because the velocities are dictated by the positions, and the positions, the difference in the positions, these are differences that play a role in the weighted average, the environmental averaging, in order to get the Cooker-Smale model. We can encode this model in terms of the graph Laplacian. So if you give me this matrix phi ij, essentially it's a matrix, so phi ij, so the graph Laplacian of phi, or the graph Laplacian associated with matrix, is simply given by what is written here. So it's the phi ij minus, we sum the term along each row and put it in diagonal, and what is written above is simply the heat equation, the graph diffusion, which is written here. Now, I should mention that this model is extremely simple. All these environmental averaging, for example, if we take phi to be uniformly 1, if it's uniformly 1, essentially this statement is that, in all the previous statement, is that the rate of change of the positions, in this case velocities, is simply the average minus VI. So it's a simple relaxation, and everything will be a relaxation towards the average. On the other hand, if phi is not just uniformly 1, then it becomes considerably more complicated. So these examples of emergence of the average, which are written here, are considerably more complicated than these two examples here, if phi is more complicated, like in the previous example I mentioned. Okay. Then let me move to the next example, which is P alignment. I already mentioned what motivated me to consider the P alignment. We simply put here an odd function of the velocities, and we get the P alignment, and this has a fundamentally different behavior than what we had before. This leads instead of the graph Laplacian to a 2P graph Laplacians, which appears in recent years in various applications. And the important thing is that the large time behavior is not exponential anymore, but polynomial. I will touch upon that later on. The last example, which I should mention, I will not discuss it anymore, but it is so important. It's an example for swarming. It's the Vic-Check model. And in this case, what we look at is orientations. And in the Vic-Check model, we change the orientation. So these are the orientation, and they change, and they are subject to fluctuations, which are written here. In fact, the original model is not written like that. I just enforce it to fit into the example I mentioned before. The original model is just an average of orientation, but if you take down the omega I, and you take into account that you take the perpendicular vector to whatever is written here, then indeed on the left-hand side, you get something which stays on the unit sphere. It's an orientation. And then this is the additional noise that you have to take into account. So you get here alignment plus noise, and this is what is behind the Vic-Check model. In fact, the Vic-Check model itself originally was with the characteristic function of the interval 0, 1, and it's a second-order model. It's assumed that the speed is fixed, unlike the Cooker-Smale model. The speed is fixed, and the only thing that we look at is the orientation. And the fundamental question in here is that there is a criticality in the role between the amplitude, I forgot here the parameter tau in front of the alignment, and the amplitude of the noise. So this ratio between tau and the amplitude of the noise will dictate whether or not we have phase transition and whether there is a global alignment or we move to homogeneous disorder. There are a lot of works in actual examples. I mentioned here particularly Ian Cousin and others. And in fact, the original examples that I brought with this Italian group, most of the physicists and biologists, they refer to the Vic-Check model. Most of the mathematical community refer to the Cooker-Smale model. Now, before I leave this example, let me just raise a fundamental question. Clearly, the communication kernel plays a central role, and the question is, where do they come from? I mean, this is not physics. So essentially, it's phenomenological. We either take a metric kernels, and you know why. In the original paper, for instance, of Cooker and Smale, they choose phenomenologically a decreasing kernel simply because it fits our tendency to think that whatever goes away with the distance, the influence goes away, decays. Another thing is observations. So for example, I mentioned already the topological kernel, depending on the crowdedness, are more realistic than metric kernels. There are random-based protocol communications, and I mentioned the ELO ratings and the phototaxes, and there are other examples. In recent years, these kernels are learned from the data, very fashionable, and then there are some higher order principles that I will mention later on, where the kernels are derived from higher order principle like entropy principle and anticipation. So talking about anticipation, let me move now to the underlying model that promoted a lot of this discussion, and this goes back to 1987 to Craig Reynolds, and he, among others, suggested the so-called three-zone model. The idea was that in order to get a realistic model for the dynamics of birds, he suggested the dynamics which consist of three rules. One rule is alignment, which I described so far, and he described it as steering towards the local averaging heading. That's what we've done so far. But in addition, he took into account repulsion in order to avoid local crowding, and attraction or cohesion in order to keep the group together. So this is the three-zone model of Reynolds. And one key, so repulsion and attraction are familiar to us. Alignment is a key feature here. And the following simulation is, I think, beautiful simulation to show the importance of these three components. So what you see here are sort of voids, birds-like object, as they called by Reynolds. And you see something which is a realistic simulation for birds, in the sense that first of all, you get flocks, they get certain tendency, they do not collide, as I promised, and they align in certain directions. Now, if you wait long enough and you turn off now the alignment, well, there's still repulsion and attraction that is familiar from particle physics, but this is clearly missing some important feature that we are looking at when we consider flocking. And the feature that is missing is the alignment. And this is to show that alignment is indeed an important feature. Okay, I will not wait for the rest of this movie. I just mentioned that Craig Reynolds won for this model the Academy Awards, the Oscar for technical achievement. Okay, here's the anticipation model, which derives the tree-zone model in systematic manner, derives the tree-zone model. And the idea is that we look at these particle systems, the usual particle system, involving positions and velocities. And the only change from the standard n-particle body system is the following. We take the system to react not to the current position, but to the anticipated position. So if x is the current position, but by x super tau, I denote the anticipated position, the position which is anticipated in a small time away from time t, say t plus tau. Now, if we take this simple system and we take into account that anticipation is something which is prevalent in social dynamics, in living organisms, in mean field games, in robots, so it's reasonable. And then if we expand this term in tau, so the first term, expanding this for the first term when tau equal to 0 gives us these expressions. And this expression, which we did not meet so far, represent repulsion and attraction depending if u prime is positive or negative. So it's attraction if u prime is positive, repulsion if u prime is negative, and that's exactly what was encoded in the tree-zone model. But there is one more term, the next term, which involves in tau, and it's the second term, which is given here. And now the phi ij involves the Hessian of the scalar potential, which is written here. So the potential here, there is a radial potential, and there is a Hessian of this potential. So now the phi ij are not scalar anymore, they are matrices. And indeed, it brings us to the question of what happens with alignment with matrix coefficients. In fact, these are matrices of special form. They are rank one modification of the identity matrix. So there's a lot of structure hidden behind what I'm telling you, but there is no time. So here's a typical example when I'm thinking about the potential that we have here in mind. Okay, it brings me to the fundamental question of short-range versus long-range interaction, which I will spend the rest of this talk, because I think that this is an important question, because this is a question. So let me tell you why I would like to discuss this question. The scenario is the following. We know what to do in the mathematical analysis for long-range interactions. However, the realistic models are short-range, and we know relatively little about the short-range interactions. So this is clearly one of those key questions where there is a gap between what we are able to do in the mathematical terms and what we should address from in the physical reality. So let's see, first of all, why this question emerges in the mathematical analysis. Let's take the p-alignment model. This is what I mentioned before. This is sort of a p-alignment based on the Cooker-Smale model. And we would like to study the large time behavior. And here it will bring us to the question of connectivity of graphs. So this is the model. And below this model, there is a graph. These are all the positions, xi, which are connected to each other. So this creates a weighted graph. And what I would like to consider attached to this dynamics is the energy fluctuations, which are defined here. So it's the double sum of the Vi minus Vj squared. And these arguments are sort of prevalent to many other models. Okay. So what happens with this, the rate of change of these energy fluctuations is that they are bounded from above by a negative quantity, which involves two terms. First of all, it's the pth power of the same energy fluctuations. So with p equal to 1, which is the usual Cooker-Smale, you get here essentially the Gronwell inequality. But in front of it, we get this scalar quantity. Let me zoom in front of this quantity. The other are just scaling. This quantity is the following. I will assume, first of all, that the interaction kernel is bounded from below by something which is metric. If it is metric to begin with, then K and phi are the same. But I would like to take into account other kernels as well. So what really matters here is the distance between two agents. So this is the K of the distance. And in fact, not only that the K of the distance between the two agents is important, what it really matters is the K of the maximal distance, the diameter of the group. So this is denoted by capital D. So we see already that by p equal to 1, we will have to integrate this quantity, and we would like to, the integral of this quantity, we would like it to go to infinity. If this integral will go to infinity, the fluctuations will go to 0, and then this means that something will emerge because everybody will get, at least in the sense of velocities, to the same velocity, to the limiting velocity, and this is the emergence behavior that we are looking at. Notice, by the way, that if p equal to 1, there is exponential decay. If p is greater than 1, then there is polynomial decay. That's a completely different story. But we immediately zoom into the fundamental behavior here of this quantity of k and the largest and the diameter of the problem. And it gives us an unconditional flocking, whether we are talking about metric, topological kernel, bounded, singular. It covers all cases except one. If k has finite support, then clearly this integral will be finite. So clearly short-range kernels are not covered by this general framework. And this is not just a coincidence, it's a fundamental difficulty, which is precisely the reason I'm comparing long-range and short-range. We know a lot about long-range interactions. We know rather little about short-range interactions. So let's take the case p equal to 1, for instance. So what I claim is that if all the velocities are bounded by a constant, then clearly the diameter grows at most like t, right? And then we find out that there is unconditional flocking if the integral of k of t, k is given to us, and now we get the time. So if it has a diverging tail, if it has a diverging tail, then the fluctuation of velocity tends to 0, which basically means all the velocities will approach a limiting behavior. In particular, if we have heavy tail kernels, something which decays with eta which is less equal than 1, this goes back to the original work of Cooker and Smale, then we get unconditional flocking. Of course, this is under the assumption there is a big if here, as long as the velocities are bounded. So as long as the velocities are bounded, then we find that if we have heavy tails, then we get convergence, we get emergence, the phenomena of emergence. And now we would like to have attraction and repulsion. Well, if we have heavy-tailed potential, which satisfy this condition, then indeed this argument prevail. It's rather complicated, but I'm just reporting here what we know. Now, this includes when we have heavy tail potential, which is attractive, but when we have repulsion, then the problem is mostly open. So let me summarize these slides, which summarize the work of many other people in the following way. If we know that the velocities are bounded, and if we know that we have heavy tail kernels for the interactions, for the alignment, and heavy tail potential for attraction, then we get the phenomena of emergence, and then all the velocities will emerge in the same direction. If there is a repulsion, we do not know. In fact, as much as I am aware, we don't know much. Well, there is a big if here, so I have to address this if. So what about this if? Well, it turns out that we can control the velocity if the underlying graph of the agent is connected. So here's the statement. What we really need to do is to control the second eigenvalue of this Laplacian matrix I mentioned before. So if you remember, the dynamics itself is driven by the graph Laplacian. The graph Laplacian, the matrix of the graph Laplacian, its first eigenvalue is 0. Its second eigenvalue is 0 or not. And if it's not, we should have a diverging tail. And in this case, and this is a sharp condition, we get emergence consensus. So what it tells us here is that we need the group to be connected so that the information will propagate. And this is an if and only if condition. Here's an example. Already in the first order bounded confidence model, I started by telling you that if you take a distribution of opinions in this fashion, then they propagate into 4 different opinions. However, if we change the phi to something like that, so that we place more emphasis on the opinions which are far away from our opinion, then all of a sudden, instead of getting 4 groups, we get a consensus. So clearly, there's a dependence on what the phi is. And even this simple model, the bounded confidence model, in the discrete case, is very difficult to analyze, even though it's a very simple model. The large crowd behavior, in this case, was analyzed in this paper. Okay. So the question of connectivity is important, and it arises even in more complicated cases. Suppose we do not have just one crowd, but we have several crowds, or we have several species. The species here are tagged by these Greek indices. And what distinguishes the alpha species from the beta species is that they have a different way to interact with the rest of the world. So we have here an array of kernels, not just one kernel. And we have agents in different species, and the different agents in different species interact. And the key element for the large time behavior here is connectivity. If all these graph of different species are connected and the information propagates among themselves, then we will get the emergence of global behavior. So there is a question mark which I'm leaving here, namely, what should we do? Because there is a gap between long-range and short-range interactions. And I'm basically left an if question open there. And in order to address it, I have to move for the question from finite number of agents to infinite number of agents, namely to the large crowd dynamics. And at this point, I have still 20 minutes, am I correct?
Yes.
Okay. Let me just quote Immanuel Kant, who said that what seems complex and chaotic in a single individual may be seen from the standpoint of view of the human race as a steady evolution. And this was predicted well before Boltzmann. So this is exactly what we will do. We will take the large crowd dynamics first. To do this, we look at the empirical distribution, and we will assume that this has a limit. I will not derive it. And we will look at the moments. We will look at the moments of these empirical distributions, which I will assume exist. And these moments are denoted by the density. They are called the density and the momentum, and simply they look like this. And thanks to Sebastian Moch for this beautiful simulation. What you see on the left is a simulation, particle simulation in 2D torus of Vikshek. What you see on the right, we don't need all the details. What you see on the right is the density and the concentration, and this is exactly the macroscopic quantities that we would like to look at. So we will look at the macroscopic densities of the density and the momentum. And when we move from the P alignment model in terms of the density and the momentum, we end up with the familiar mass and momentum equation, which are given here. And they're really familiar to us because this is the mass equation, and this is the momentum equation. The momentum equation involves the pressure, which is a tensor, and the alignment term. So the dynamics takes place in a domain ST, which is the support of the density. And I will assume that the support of the density is bounded away from 0. So there is a blob of density which is bounded away from 0. This would be the assumption. And there is something about the boundary, which I just wrote here, that the normal part of the velocity is 0 simply because I have no idea to do something better. But it's clear to me that modeling this part is the critical part in hydrodynamic alignment. Now, what is the alignment term? This reflects the discrete alignment that we have here. So here is the power 2p minus 2. This is the fluctuation of velocities, and it's weighted by the density. And that's exactly what we do here. And this is alignment dynamics, which is dictated by the communication kernel phi, still the original communication kernel that defines everything. So let's take, first of all, the case when there is no pressure. So this is just alignment hydrodynamics. Now, if we take phi to be identically 1, I mentioned that before, this is simple relaxation. Everything is clear. But if we take phi, for example, to be a local function, the characteristic function of some ball, then it's considerably more complicated when the dynamics is basically enforced by local averaging. So what we are studying is everything in between. Now, what about the pressure? There is a lack of closure for the, we don't know how to close the pressure, and there is no Maxwell here. And let me quote, because I have no time, let me quote here a very influential, Vikshek, a very influential paper, from their very influential paper that they say that the source of energy making the motion is not relevant. The pressure, of course, is intimately related to the energy. I partly agree that the energy is not, well, I have to agree because I'm not a biologist and they know so much more. The source of the energy is really not relevant. However, it is relevant. I don't want to completely abandon the thermal equilibrium in the sense that I would like to enforce entropy inequality. Namely, there are fluctuations, and I have to take into account that this fluctuation dissipate. Otherwise, the model is not relevant. So I will not close the pressure, but I will have to assume something about the pressure. What I will assume is entropic pressure. Now, in order to define an entropic pressure, so this is a recent work from 2023, we have to get into the details. So we'll have to look at the trace of the pressure, which is called the internal energy. And it's given by this limit, which I will assume exists in terms of the empirical distribution. And formally, the internal energy formally satisfies this equation. So there is nothing here. This is completely the complete formalism of the internal pressure, the unknown pressure, and of course the alignment, just moving from the discrete description into the macroscopic description. But this doesn't tell us anything because I didn't tell you what the pressure is. I didn't tell you what the Maxwellian is because I don't know what the equilibrium is. In fact, there is no equilibrium. But what I would like to insist is that this equality will be turned into inequality independent of the pressure. Now, I define a pressure to be entropic if it satisfies this inequality when with arbitrary heat flux, let's say. And now, these are a few examples here that I mentioned, but let me skip it in favor of time. Now, why do I insist on this inequality? So I enforce this inequality because if I take this inequality and I add it to something which is completely algebraic, coming from the mass times u squared over 2 plus the momentum dotted with u, which is written here. So if I add these two inequality together with this identity, if you want to, I conclude that the total energy given by here, the internal energy plus the kinetic energy, satisfy this inequality. And this inequality is really a reflection of my definition of entropic inequality. So let me just pause here for a second because it's an important thing that, that is going on here. First, let's look at the right-hand side. You can see that I massaged these terms. Here's this interaction kernel. The u dot dotted with u minus u prime. So this is a fluctuation because I'm going to integrate over all the positions at x prime. So I write this u dotted with u minus u prime as 1/2 u minus u prime when I integrated dx and dx prime. So we get here a full fluctuation. And then we get here the internal energy, which appears here. And by symmetry, I can put here the internal energy and the internal energy prime. So this is a complete statement on the right-hand side. On the left-hand side, we get the rate of change of the total energy. However, I claim that the total energy here is the same thing, the rate of change, as the rate of change of the energy fluctuations. So let's pay attention. We get here 1/2 rho u squared, and here is rho u squared. Here is rho prime u squared, which is the same. Now the integral of rho u, this middle term, vanishes because the momentum is conserved. And then I added, of course, the energy on the left-hand side. And I massaged everything. I didn't do anything. I just massaged the terms in such a manner that I get that the rate of change of the energy fluctuation on the left is related to the rate of change of fluctuation on the right, weighted by the kernel of interaction. So let me summarize everything. So these are the energy fluctuations, and what we get is that the rate of change of this energy fluctuation are bounded and by minus the fluctuation to power p. I took the case p equal to 1 here, and I pull out the k, the same k that we had before, times evaluated at the maximal diameter. Essentially, I recovered exactly the same estimated as I have in the discrete case without making any assumption about the pressure except of having an entropic pressure, which is quite remarkable to my taste. So we will now assume that we have a strong solution, which is bounded from vacuum, and we have any entropic pressure. I do not want to assume, as in most of the literature, that there is zero pressure. And I claim that just by using this entropic estimate, one can deduce, of course, one can deduce as usual, that if the integral of this, the strength of the interaction at the maximal distance, if this tail is diverging, then we know that the fluctuation tends to zero, and that's exactly what is needed. The question is, how do we control this term? So, well, we do it as in the discrete case, but I'm now interested in the short range case. So what happens when K is short range? Now I can do something that I could not do in the scalar case. But before that, let me just summarize everything. I have now a hydrodynamic solution which involves the density, the velocity, and this enigmatic pressure, which I did not even define. I assume that the interaction is bounded from below by some metric function, K. I will assume that the diameter grows at most like gamma. So this is an assumption because I don't know how to control it. And then in the case p equal to 1, we get this kind of decay of fluctuation. In the case p greater than 1, we get this kind of decay of fluctuations. And the conclusion is that if this product of eta gamma is less than 1, then we get emergence to something. So what is this product of eta and gamma? Eta is the decay of rate. This is the decay, the rate of, say, communication for two agents which are far away. And gamma is the rate of dispersion of the group as they could disperse, unless, of course, gamma equal to 0. So in the case gamma equal to 0, there is no dispersion. And then, of course, we get unconditional flocking. Okay. So here is an example which due to lack of time, I'll just tell you that if you have heavy tail, one can prove that indeed gamma equal to 0. This is most of the literature in the last few years, but it is done here in sort of in this general framework. So the conclusion is this: if eta is less equal than 1, then gamma equal to 0, and clearly eta gamma is less than 1, and then we are done, and then we get flocking, and then everything is okay. But this means that the interaction again is global, and it applies even when we have a matrix interaction, which is not so trivial. But I'm still stuck with my problem that I cannot get rid of global interactions. So what I would like to do now, and then I will conclude in the last few minutes, is I would like to take a different kind of family of interactions where the interactions, on the one hand, they have a heavy tail. On the other hand, they have singular head. So here's the singularity. D is the dimension. S is a parameter between the dimension divided by 2p. And this is a bona fide qualified singular head. And the singularity of the kernel when two agents are very close will play an important role. So in this case, we have the dynamics, which reads like so. We have the momentum driven by the unknown pressure, entropic pressure, and it involves the principal value of this kind of singular interaction. This is the singularity here, and then we have the tail there. So this is a singular P alignment communication, and actually the singular part here admits a commutator form and so forth and so forth, so on. The important thing is that the singularity coming here implies that we have bounded entropy, because this quantity integrated in time is finite. In fact, the integral of this in time is exactly the decay of the fluctuation that we had before. So this quantity that we have here is bounded in time. Now, the bounded entropy, in other words, tells us, if you look here, that the Sobolev norm, the fractional Sobolev norm of order S in LP is to the power P is bounded by a quantity, a finite amount. And it is here that I invoke the Gagliardo-Nirenberg inequality, which tells us that the fluctuation between 2 points for the velocities is bounded by the fractional Sobolev norm times the relative distance. So I translate it to the statement that the rate of change of the diameter, which is clearly bounded by the maximal fluctuation of velocities, which is bounded by the Sobolev inequality, times the diameter to the power S minus theta. When I solve this ODE, I conclude that the diameter grows, well, at some finite rate, which is given here, which we are not interested. In fact, one can use iterative improvement and get a better constant here for the gamma. So I get a pointwise control without closure and without a maximum principle. And this implies that once that we have this gamma, that now we can play with the eta and the gamma I mentioned before, and that's exactly what is done here. And here's the conclusion. If we have a singular head where P range between 1 and 3/2 and heavy tail, which is restricted in this fashion, then we get an optimal bound for the diameter, namely the diameter may grow, but then by iterative refinement, we find out that it does not grow at all, the iteration decay, and therefore we get the emergence into the final limit. And this is without assuming anything about the pressure and without assuming anything about the large tail. I did not use the large tail behavior, but I do assume that P ranged between 1 and 3/2. And I needed that the dimension is less than the 2P, so this whole discussion is restricted to the 2-dimensional case. And the problem is open for 3 dimensions and up. And this is not just technical difficulties. There is some inherent essence, which I don't understand, that what happens in D equals 3 and up. D 3/2 is a critical even in the pressureless case. I should mention that here. And one can use fixed point iteration to improve this diameter to get something slightly better. But yeah, let me just save it from the discussion at this late hour. Okay. I should mention here that these arguments apply also in the case that you get not just one crowd, but you get multi-species behavior, the same arguments about connectivity and the tail and the singularity, and that's exactly what's going on here. And then there are other arguments about short-range interactions when the interaction is not metric, but topological. I mentioned before about topological interaction. It turns out the topological interaction, at least in the 1D case, are better than metric. And in this fundamental work with Roman Schweidkow, we were able to show that if the density is bounded from below, then even when you get short-range interaction, then the dynamics should flock. But this is restricted to 1D, unlike what I've shown you before. Okay, let me summarize by mentioning just a general overview about the different questions that arise in different fields in this context. In biology, we are talking about flocks and swarms. The agents are different, and the question is whether the observed patterns are system-specific. These questions arise in physics. We have ensembles, and we try to find similarity, or at least the physicists. They look at thermal equilibrium, statistical mechanics, and they try to classify patterns of collective motions. In computer science, there's a lot of literature which is driven, of course, by dynamics and spectral theory of graphs. In engineering, I already mentioned several examples, but I did not do anything beyond that. And then what I've done here, I try to emphasize the interplay between long-range interactions and short-range interactions. And we are right now in the part of the understanding of the, I think, important questions. So let me conclude here, and let me thank you for attending this talk. And yeah, this is what we would like to simulate, but we are not there yet. Thank you.